Cool. Okay. Um, Hello. Today I'm going to be kind of going back and expanding a bit on the last binary exploitation lecture. So I believe you left off learning about shell coding and how you can kind of take control of execution by writing your own code and jumping to it and then, doing kind of whatever you want from there, probably popping a shell or something. So now we're going to take a look at kind of what mitigations exist in the modern era to prevent that and how we can kind of avoid them in the constant, cat and mouse game of mitigations and getting around those mitigations. So um, let's just say, in our, hypothetically, we have control over the stack. Before we saw like, okay, what if there's a win function that just does what you want? Um, that's not really going to be a thing in the real world, maybe, but generally speaking, you probably won't find that for any reason. Shell code, that's something we talked about, but as I mentioned, that's sort of in the modern era, that's not really a thing anymore. It's more of something like a remnant of the past. So let's take a look at what the modern era looks like. So generally, there's a few names for the first mitigation we'll talk about. It is either called no execute, data execution prevention, but basically, if I let me just go to my demo screen. God, say we have a running program. We take a look at what memory mappings look like. You'll see a permissions column, and so you'll see read, or a dash means it's not permitted, but read, write, execute. And so with shell coding, you need to have a page of memory that can allow you to write and execute code. So you can first write your shell code and then you can execute it. So what this mitigation does, NX, no execute or data execution prevention, um, basically all of your memory is by nothing is by default mapped to have write and execute permission. So it can have either one or the other. And what this means is that then if we were looking at writing our own shell code to the stack, stack data is mapped no execute. So you can write your shell code there, but if you try to, set jump to it or whatever, get the instruction pointer to start pointing there and executing there, it'll crash because it doesn't have permissions to do that. So yeah, unfortunately, that kind of gets rid of shell coding. It is possible to have like you can tell your program that you want to have read, write, execute permissions, but it's not really something you'll find all that often. But it is, it's possible, but it's not a default. So how do we get around this? Well, sure, we cannot write our own code, but if you think about a running program on like a modern computer, you've got your basic binary that you've written. Maybe it's like a really big program like Photoshop or something that has all sorts of stuff going on. You also got tons of libraries. You got libc by default on Linux. Maybe you have a bunch of math libraries, whatever it is. There's a lot of code that's already, mapped as executable, that's already written for you. So what if we can kind of piece together bits of that code to form a larger program, or that can perform some tasks that we want? So one example of this is return-oriented programming, or ROP. And so you have this notion of, on the stack, you have your return pointer. So a function is called, it puts on the stack the address that it has to return to once it's done with that call. And so when it's done with the call, it will execute the return instruction, which then pops the return address off, and then that's where it will jump execution to. So, you know, what if we could find a bunch of small little, what we'll call gadgets, that do little bits of computation and then return, and then we can kind of chain them together in a row on the stack. So it will execute one, pop pop the next one off, execute that one, and so on. And so this is just an example of some gadgets you might want on a 64-bit machine. So yeah, basically they're all going to be ending in a return because you need to return the next thing, unless it's a syscall or an int 80 if you're on 32-bit. Those are pretty much the same thing. They're just doing a system call. If you're doing like execv or something, you don't really care if it returns after that. You just, because you're executing an entirely new program at that point. But yeah, so and you string them together, you get what's called a ROP chain. So when you want to do an execv call to get bin sh, you want your registers to look like this. On 32-bit, it'd be a little different. Racks would be 11 because that's the syscall number on 32-bit, but here it's 3B. So you want your string bin sh, whatever you want to execute in RDI, RSI, RDX, or 0, and you want to execute a syscall. So with ROP, what that would look like is first, this is the stack. You have your first gadget, which pops RDI, pops RX, and returns. That's all it does. And then, you have your pointer to bin sh, which you want in RDI, and then your syscall number, which you want in RAX. So we'll step through this. So presumably this is like overwriting the return address of some function call. Now it's returning. Oh, it pops that address off. Then it jumps to our gadget. Pops off RDI, pops off RDX. So it's filling our registers. Now it's at a return address, pops off the next return address. Now it's at our next gadget, pops off RSI and RDX, and then finally gets to syscall. So that's basically what it looks like. Let me see. Okay, cool. So in the first example we're going to look at, we've statically linked in libc. So basically, you'll always have libc if you're on Linux. And or on Windows or on Mac, there's like usually like a standard library. And so as we were looking at before, we have these gadgets that we can execute, but we can also, for example, say you wanted to do a write syscall or something. libc has wrappers for all these syscalls that just take in normal arguments. It'll load up the write syscall number. It'll if say you wanted to do like execv, there's a system function in libc that just takes in a string, your first argument RDI here, bin sh, and it will fill up the other two registers with 0, and it will do the write syscall. So a lot of times what you can do is you can just literally return right to the beginning of those functions, as opposed to writing a longer ROP chain to fill the registers and do the syscall manually. So it's called ret to libc. Ret to system is what you would call like returning directly to the system function. And it's also a really cool company. So first, if you want to go to this URL and grab that zip file, there's a couple exercises. If you want to pause the lecture and try to work on those yourself, you're welcome to, and I'm just going to walk through them now. ROP Gadget is a really great tool for finding those gadgets that I was talking about. So it'll just scan your file and look for anything ending in a return instruction. And I'll show you kind of how to use that too. So let's go back here. Okay, so this is ROP1. This is how it's compiled. We've got our win function commented out, so we can't use it anymore. And so, yeah, let's take a look. So it looks like it prints out some stuff, has a 64-byte buffer on the stack, asks you to give it a string, you give it a string, it fills up the buffer, and then it returns. And it doesn't really do any checks. It will just scan for any arbitrarily length string. So we can do some stack smashing here. So, and I've written kind of the outline of let me just fix that quickly. So here we have just the basic outline of an exploit script. So first we have a pause so that we can attach with our debugger. Then we read until the call you is printed out. So what do they call you? Then we send in our wrap chain, and then we just let we switch to just manually interacting with the program after that. I believe some Pwn tool stuff has already been covered, but yeah, you can also just read the documentation. It's a very useful and pretty straightforward Python library for writing exploit scripts. So I'm actually just going to move it here and then cool. Okay. All right. So we got this seg fault. So so first, right now we're just sending in like 64 A's. That's gonna like do a okay. Let me just take a look here. So I want to kind of step through. Normally, you'd probably want to open your program in IDA, but or something like some disassembler, but small, so it's fine. So let's see. Okay, so if we look here, it shows you all the calls, printf. Okay, scanf. This is where it's reading in our information, and then it prints some stuff out. So here is where I'm just gonna put a breakpoint because I just want to step through it and kind of show like what's going on. So and also here, so we're sending in 64 A's, which is filling up the buffer. So let's see what happens if we like send anything else after that. So let's do some B's and some C's. You could just do a bunch of A's, but I like to do it this way so that you can kind of see. Also, it's 32-bit in case that you didn't notice that, but that's why I'm doing 4. But if you're ever working with 64-bit, you want to do 8. But anyway, so the reason I like to do this is just so that like you can see, you control all of those like letters like 4-1, 4-2, 4-3, but then you can kind of also see like the different parts of it. So like you can kind of like it's just visually more pleasing to look at. So let's take a look at what happens when we run this. Okay, so now we're at kind of the end of the function. Let's start stepping through. Here we see our A's and the B's and the C's. So it looks like it's restoring our stack frame, pops some stuff into ECX, EBX, EBP, and then now it returns. So, okay, interesting. So now it looks like our stack pointer is filled with B's. Almost all B's. So that's kind of funny. We just sent in a bunch of B's. So what's happening is right after the buffer on the stack is the address of the previous stack frame, then is the address of then is the return address. So let's scroll a little bit back here and see. Okay, so it looks like first it pops ECX off the stack, uh, ECX off the stack here, so that's where our B's are coming from because that's where our B's are on the stack. And then it pops some other stuff, and then it sets our stack pointer to whatever ECX is -4. So that's why it's not like quite entirely all B's. So we want to make sure that we're not corrupting our stack pointer because then it will just crash right away. We want it to actually return somewhere. So we can see that here, this address is where our C's are starting. And so our C's are where we might want to, that's kind of where the return address should be and where we want to start writing our route chain. So we want the stack, when we want when we hit the return instruction to return here. So if you notice here, it also does a -4. So we want to just copy this guy, 78, and we will, just for the sake of like making this cleaner, I'm just going to do it on a new line. Cool. All right, so let's take a look what happens when we run this. Attach. I'm terrible at typing. Got a breakpoint. All right, so we pop into ECX. So we see here we have our that same address that we put. It's going to go into ECX. Now we pop into EBP, whatever, doesn't matter. And now we have our load effective address LEA instruction. Now ESP is right where that address we put -4 is, which is where our C's are. And so now when we return, we're going to get PC is 4343, which is just C, hex code, or whatever, ASCII code for C. So that's great. Now we control where the program counter is, or EIP. So now we can actually start writing our route chain. So I'm going to just kill this program, and now we're going to take a look at route gadget. So route gadget is a really cool tool. Lot of different, options for like finding or like adding constraints to finding route gadgets and stuff. We don't really care about that right now, though. This is pretty simple. So you can also, there's also like, I'll just briefly mention, our gadgets that we're looking for all end in like a ret or return, but you can also use gadgets that end in a jump, or something like that, because like say like it's like a jump to racks or something, or some register that you control. You can kind of also, like in situations where you like have to write a kind of weird or tricky route chain or something, you can write a job chain, which is just like kind of weirder, but it is definitely a thing you can do. So but we don't really care about that in this case. The other options are all just kind of, you can read them, they're pretty self-explanatory. So binary. So you use the binary flag to specify which binary you want. So we're going to do ROP1, and we're going to put it into gadgets.txt. When I run this, it's going to take a little bit. That's kind of why I'm putting all the output into gadgets.txt, or wherever you want to call it. Basically, rather than grepping through the output and having to run ROP gadget every time, you can just like save into a file and then you're good. So let's do grep for like pop edx in gadgets. So you can kind of see the output. So it will tell you the address in our binary of where all the gadgets are, and it will show you what the full gadget looks like. So you could be like, here's one, pop edx, pop ecx, pop eax, then it jumps somewhere. And so, and then grep is just highlighting the thing that we're looking for. So that's basically what the output looks like, really useful. So now we can use that to start writing our route chain. So first we want, so if we go back to our slides, a little bit different because it's 32-bit for our binary, but the slides have 64-bit, but kind of the same. So first we want racks to be our syscall number. So as I mentioned, and I'll just show, syscall for execv, this is just like a, you can just Google like syscall table and stuff to find all these numbers. I don't remember them all by heart, but we want to do an execv syscall. So we look here, EAX is 11, which means the syscall number is 11. Then EBX is where we want to put our pointer to bin sh. So cool. Let's look for, so we want to just focus on getting EAX to be 11. So let's look for a pop EAX gadget. And we can just make this easier. You can also, it's also useful because you can put like, say you want to look for like a kind of a weird gadget that does like a bunch of different things. You can kind of like grep them together, so like it doesn't have to all be like in the exact right order. It's really useful, like just kind of like sometimes you might be like doing a really hard challenge or writing an exploit for some really difficult like bug or whatever. And you'll just be like scrolling through wrap gadgets and like looking for like some peculiar gadget that does exactly what you want. So yeah, but here we have, all right, that looks good. We have a gadget that does what we want. So one thing to notice, and this is kind of like just an annoying thing about sending stuff like whatever like to your program, is that, so let me just open the source again. So it's using fscanf to read in our string. And the way it tells that the string is over is that there's like a new line or something like that. And so a new line in the ASCII table is 10 or A. And so if our ROP chain had not like A, the literally the character, but like OXA. So if any of the bytes that we send it are A, it will just stop reading the rest. And so B, OB, which is part of our address, unfortunately, um, is that the address of this gadget, unfortunately, is like vertical tab, I think. So that's also gonna stop it. So we can't actually use this address. So, but like what I was going to do was pop EAX and then put like whatever 11 after it and just pop it into EAX. That way, the other thing we could do is if we look here, EAX is 0. We could just do a bunch of like increment instructions or something, like 11 of them to just like, increment it 11 times. So let's look for that. I've like totally, used this address or whatever, like addresses like this with bad bytes in them, and then like, your exploit doesn't work and you're like, why is this happening? But yeah, that's just something to keep in mind for. Um, it's just whatever. It is what it is. So let's look for an inc AX. So many. Sweet. Okay, so that's one. So that looks pretty good. So let's, well, put a bunch of those. We'll do times 11. Cool. Sorry, let's start stepping. So cool. So we see now on the stack, instead of the C's, we just see a bunch of like increment instructions. So we return, we jump to the next, instruction, or it pops the first return address off the stack. We see it's now at our gadget, which is inc.ax. That's 1. Returns, pops the next one. It's 2, so on and so forth. And now we've got B. And now it's where our C's are, and now it's going to crash. So, but I mean, you can see this is the idea, and we've got one of our registers in the right state. So that's great. So the next thing we want to do is get EBX to be a pointer to where binsh is. So let's look for a gadget to do that. Think of EBX. And let's go. Sweet. Grab that guy. And we'll put that in our wrap chain. Cool. And now it's going to pop something off the stack. So we now, like, because we're literally, this is what we're writing to the stack, we want to put like the next thing is what we're popping into EBX. We don't have an address for binsh, but so I'm going to put like a placeholder for now. Whatever. But so after a wrap chain, I'm going to just write that string, and then I'll look back, get the address, and we'll fill this placeholder in later. But for now, let's just leave it at that. And cool, let's run the program, see where we're at. Step through, return, bunch of increments. And now we get to our last gadget, which is pop EBX. There's our 31313131 return to C's. Okay, great. So it's crashing, but now we can fill EBX. So now we want to set ECX and EDX to be 0. So let's look for those. EDX. Cool. Okay. So that looks like a pop EDX, or I'll look for ECX first. Huh. There's not one that just does that. Huh. All right. Well, here's one that pops EDX, ECX, and EBX. So we can just use that one instead, actually. So this is our gadget to pop EBX. There isn't one that just pops ECX and returns, but there is one that pops the 3 registers you want. So, I mean, we'll just use that. So, chain added. You don't have to put comments and stuff with the exact thing that the guy is doing, but I usually just do that for the sake of like keeping track and keeping organized so I don't mess something up and then not know what anything is doing. So it's popping 3 things, so now I want to put 2 zeros on the stack, so it's going to pop the first 0 into EDX, the second 0 into ECX, and then the last thing, which is our placeholder address for binsh, into EBX, and it will return. So cool, let's take a look at this. Step through, doing our increments. Now we get to EDX. Okay, so this is our longer gadget, so now it gets EDX to 0, ECX to 0, and then EBX to our placeholder. And now it's going to crash. So now we have basically the registers are exactly what we want. We have to fill in the placeholder for binsh later, but we'll do that after we do our last thing, which is just to find an int 80, which will actually perform our syscall that we've just set the registers up for. So here's our int 80. And let's just pop that at the end. I hate this. Okay, and great. And now we'll put bin sh at the end of our route chain. So we'll run it, attach, continue. Now we'll step through everything. Another option is that you can just like add 5 and then 6 to EAX. It doesn't really matter. That's just like what I am doing. But yeah, it is kind of annoying to have to like step through it all the time. So, okay, great. So now we get to our 80 gadget. It's not going to do anything because the string argument that we're giving it is just nothing. But if we look here, this is the address of where binsh is. So if we go back now, we'll change that here. We'll run it again. And, oh, what? Hold on, let me run that one more time. Set our breakpoint again because I quit GDB. All right, now we'll step through. I think the exploit just worked. I wasn't paying attention to what happened, but all right, let's just do our pops, or increments, sorry. Now our pops. EBX is now pointing to binsh, return int 80, and now voila, we have our shell. So there you have it. That's a very simple route chain. Um, yeah, it's definitely more annoying doing this than just returning to system, like I mentioned. So you could just do that instead. But for now, this is a good demo. So okay, cool. So let's keep going. So we've talked about the first mitigation, which is data execution prevention, whatever you want to call it. Just you can't write and execute to the same memory. So that's one. The next one is, if you notice in my exploit, I have ASLR equals false. So ASLR is another mitigation called address space layout randomization. So if I'm just going to open the next, or I'll start, well, no, never mind, I'll do that later. So basically, every time you run your program, your operating system's like, all right, we got to figure out like, it's loading its library. It's like, all right, this is where we're going to put, our main binary. It needs libc. Okay, we'll map libc to this address. We'll map, it needs this crypto library or a math library. We'll map that here. The stack, we need to put that somewhere. So what I'm referring to is if we just do like, map um, these addresses where it's like putting stuff, it has to like figure that all out. And so for us, we were kind of just assuming everything would always be in the same place. So we have in our exploit, like hard coded addresses to the stack or to into our binary or whatever. And so in this case, ASLR is off. We can totally do that because it will always reliably put the same thing. It will always put the stack in the same place, the heap in the same place, whatever. But what ASLR does is it says, okay, some of this stuff we can actually move around. So if we look at our main whatever, our main function, so it's calling into hard coded like addresses, right? So like here is like the set vbuff function or whatever puts. So it can't move this thing around because if it does, then these addresses will be invalid and the program will crash. But for the stack, it doesn't really depend. Our program doesn't really care where the stack is. It just uses it to like push and pop stuff. So the without ASLR, if we turn this off, or get rid of that, it'll just default to on. Let's do a VM map. So without ASLR, it can just put the stack anywhere it wants. So here it could be this run, it's like FF95D. Let's run it again. FFB49. So part of this is because sometimes it like hard coding where things are is just sort of bad practice anyway, because then you don't really have flexibility. For example, say you have like you're assuming the heap is in one spot, um, and then another thing like a library you're importing is assuming the heap is at like another spot. Well, now you're kind of screwed, or whatever. So that's like you kind of want to be able to move stuff around. But also, it's a really good security mitigation because now if we turn ASLR on, our exploit won't work. We are assuming that we know where the stack is here and here. But really, if we run it again now with ASLR like turned on, it could be anywhere. And then here, like, it will try to, use these addresses and it will just crash. So um, this is just kind of, gonna make things a little bit harder. But as with the last mitigation, a couple of talented hackers can pretty much get through anything. So how are we gonna defeat ASLR? So let's just say we somehow have leaked the address of something in libc. So here we have libc is statically linked, so you're not going to see it mapped. But if we go to like, I'll just whatever open the next exercise, rough 2. So I'm not going to show you quite yet what the next exercise is, the source or whatever, but um, just know that it's not statically linked. So now we actually have libc as a separate like LinkedIn thing. So um, let's just say like, we want to, we're using what, okay, so actually first I should say, before we had statically linked in all of our gadgets, or sorry, we had statically linked in libc. So all of our gadgets, so like most of the gadgets we were getting were probably from like libc functions because our actual like binary code, like just like the main function, doesn't really do that much. There's not really that many gadgets there. But libc has like a ton of gadgets. So we statically link it in, and we can just do wrap gadget on our binary like normal. But now, because it's not statically linked, all of those gadgets are just in libc here. So now, before like we could just sort of hard code those addresses, now we don't know where they are. Similar with the, with the stack addresses. So let's just say we do know where like one thing in libc is. So like say there's a, like print, just print read. So read is just a function in libc that is just a wrapper for the read syscall. It takes in, a file descriptor, a buffer, a length, whatever. But say we know where this is. So, or I'll just go back to the slides because it has a better diagram. Or fine, puts, whatever. That's another function in libc. So say you know where puts is. Even though the address of puts might be random, or the address of libc might be random every run, the stuff within libc will always be at the same offset relative to the start of libc. So if you think of libc, or think of any like whatever binary or whatever part of like, yeah, fine, libc or binary, whatever, memory region, as just like a chunk of like self-contained code or whatever, it won't change. It won't rearrange where functions are within libc because it's just like in a file that it's like mapping in. So it can change like which virtual addresses map to the like like, or like where the start of it is, so it can move it like up and down in memory, but it can't like change things within it. So puts will always be at the same offset from the beginning of libc. So even if we run it again, the address is different. This offset here, the 68F90, will always be the same. So we subtract that offset. Now we know where the base of libc is. And so once we have the base of libc, we can also find out, just the way we found the offset of from puts to the base, we can find out the offset of like system or any of the gadgets, for writing rock chains or whatever. And then, so even though we can leak, if we have a leak of which is, just what you would call like knowing, even though you're not really supposed to know where the addresses of things within the program are, but say you somehow do know the addresses, the address of puts, you have that leak. Now we can figure out where anything else in libc is. So yes, ASLR makes your life more difficult, but you just need a leak for like everything that you would want the address of, and then you could figure out where everything else is pretty much. Um, this is just disgusting. I don't know. This is just kind of demoing like what we were just looking at, but whatever. It just looks bad. This part of the slideshow I think was from last year, so we hadn't quite gotten to Pwn tools yet, but I'll just skip through this stuff. And okay, cool. So now is, I think, a good time to go and walk through the ROP2 exercise. So if you want to do that yourself, just pause the lecture, go ahead. I'm just going to walk through it now, so you're welcome to like just try to figure it out on your own first. Or if you just want to see the walkthrough, that's all good. So sorry, I'm just going to rearrange this window. So let's take a look at the binary. So as I mentioned before, it's not statically linked, so we can't just rely on all of our gadgets being in the same place. ASLR is on now, so that sucks. But if we look here, looks like the same thing, but there's a small change. At the end here, it's printing out the address of stdin. Stdin is basically just a structure within libc. So it's basically just giving us a libc leak, like with puts, except it's just a different thing. But it doesn't really matter. The same technique still applies. stdin will always be at the same offset from the beginning of libc, so we can just calculate that offset, and then we're good. So let's give this a run. First, actually, let me just change the exploit script to just like use this one now. I'm just going to comment all this out. Or, fuck. Okay, there we go. So let's give this a run. Oh, right. Sorry. Let me just actually get rid of this thing because it's cutting off some of our output. Okay, there we go. So let's look at where it's printing stuff. Okay, so let's look at this address. So it looks like it's printing out like an address. So let me just like attach to this thing. Or actually, yeah. No, wait. Goddamn. Gotta get rid of this thing too. Okay, so while it's waiting for us to enter stuff, let's just like pause it for a second. Okay, so it's giving us this address. So let's just see what this is. So vmmap is a really useful command. It will just show you the memory layout of your program, but also it's also not in standard GDB. It's like you have to use PETA or whatever, but that's not too hard to get. But you can also do like proc mappings or something. But anyway, just for the sake of demonstration, I'm just using vmmaps because it's easier. But if you put an address as like the argument to it, it'll just show you if it's in any of those ranges and which one. So if it's not, it will just show you nothing. But in this case, it says that this address that it's printing out is here in libc. That makes sense. It's stdin is in libc. So let's take a look at some of that memory. And sure enough, we see this is just like a longer kind of whatever name for it, but basically this is stdin. This is just sort of some flags for a file structure. Don't worry what that is too much. We don't really care what stdin is right now. We just want to figure out how to use that leak to figure out where our gadgets are. So we take this address and we say, okay, let's just write a little thing here. The hex is just going to convert the number to like hex form. You don't have to do that, but I'm just doing it because it looks nicer to me. So we're taking this address that we have. We want to find the offset from the beginning of libc. So, well, this is where libc starts. Let's grab the beginning. And there we go. That's the offset. So if we just always take our leak and subtract this offset from it, we'll always be able to figure out where the beginning of libc is. So our exploit is then going to want to dynamically figure out where like gadgets are and things like that by using that leak. So I'm just going to actually get rid of the source and just open the exploit here. So we want to read in that leak so we can actually use it in our exploit. So let's say up until here, we'll read up until here. And now we'll say leak is read until this ... thing. Now we'll just print out our leak. And okay, so looks like it's working. There's like an extra space in the beginning. This is just like stupid string formatting shit, but we want to get rid of this and convert to an actual number. So we'll just do like, there's always going to be like 8 characters here. So if we just do first we'll include that space so it doesn't appear in the string, and then we'll do just get the first 8. Cool. And we'll also make sure, oh, actually, okay, yeah, so we can just do int and make sure base 16. So int is just going to convert any string to a number. It's like a Python built-in thing, in case you've never seen it before. And then the second argument is optional, but it lets you specify the base of the thing you want. So I think if you do 0, it will just auto-detect it, but if you do 16, it will just assume base 16, and that's what this is. So cool. So now it's just printing it out as an actual like integer, and so it's not going to like format it specially for us. But if we do, now we can just say, okay, the libc base is at leak minus whatever our offset that we had was. And now we'll just do, actually you can do UI dot, or no, what is it, log.info or something to like kind of print it out. It's like a built-in Pwn tools function to just like pretty print stuff. So we'll say libc base at libc base. Cool. And sure enough, libc or whatever vmap, this is just like, it's just shorthand for it, but DC 9000, perfect. So now we know where libc is. Okay, great. So now let's start actually sending in some stuff. So I'll send in our ROP chain. We'll send in our B's. Our C's, and just like see what's going on. Also, gotta set that breakpoint here just to make sure. Cool. Okay. So, okay. Sorry about that. I had the wrong file. That was like an older one. Just realized it as I was doing it, but whatever. So the right file is supposed to leak two things. First, it's supposed to give stdin as we were looking at before, but it's also supposed to leak name, which is a stack pointer. So that's like, you know, before in our exploit, we knew where to, like we were overwriting our the address of the last whatever stack frame. And so we now won't know that because of ASLR, but we can try to parse it from this leak. So actually, whatever, just in case you want to see it for a second more. If you look, before also name was here. I think it was maybe like for ROF3, like in the middle of writing that. I don't really know, but anyway, yeah. So the main difference is just that now it's leaking two things, and also name is back on the stack. So let's get our exploit open here. And now this parsing won't work because it's a little bit different, but so let's just, excuse me, ignore that stuff for now. Cool. So now it's printing two addresses. In case, just to verify, we'll do, we already saw that stdin was there, but whatever stdin was, but now we'll look at this. So gotta, yeah. So it's on the stack. So it's, you know, I mean, you know, not that big of a reveal, but yeah, just to confirm. So let's now let's go about parsing our leak. So sometimes it's easy like this where you just convert an integer. Sometimes it can be really hard. Leaks can be like kind of an interesting like aspect of a challenge or of a bug. Sometimes it's straightforward to get them, sometimes hard. Sometimes you can leak part of something. So you can maybe leak like, you know, what if you had this part, but you didn't, or, you know, what if you had like this part, but you didn't have this part? Like, could you brute force it? Maybe if you're on 32-bit, you could just brute force the whole thing, whatever. But right now it's pretty straightforward. So we're gonna first read this part in. We'll say leaks equals, just read the rest of the line. Now we're going to say libc leak equals name or might be cool. All right, name leak or buffer. I'll just call it buffer. Yeah. And I'll just do print or just make this shorter. So, all right, cool. So we're um whoa. It's been a while since I've used Vim. Trying to get rid of the dot 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 at the end. Oh, right, there's the formatting. All right. Uh, did I just guess it right? Huh. All right, cool. Well, there you have it. Um, those are our two leaks. So, and we want libc equals libc or whatever int libc 16. So we're going to convert it to an actual raw integer from a string, and we'll subtract our offset. So we'll find, we'll say, okay, libc here, attach. So this is our leak. You have to have the OX, whatever. We'll do VMAP. Okay, great. So now we'll do that to get the offset, and we'll say buff equals int 16, convert that. Right, okay. And then we'll just convert these to hex numbers. All right, great. So now we have our leaks. Cool. Just wanted to make sure I actually was like parsing that right. So that's nice. Now we can actually start sending stuff in. So yeah, basically it's printing out the leaks. I'm just reading them in. I'm converting those, like it's as a string, I'm converting those strings to like raw numbers that we can actually like manipulate and like do math with in our exploit. And then we could use that to dynamically resolve, say like we want to know where a gadget is, we can just add the offset of that gadget from the beginning of libc, for example, to get the actual address live. So we're not hard coding, we're actually dynamically resolving those addresses. And then I'm just printing them out because it like looks cool and it's all hackery. So, right. So another thing is that, as I mentioned before, this is not statically linked. So now we are going to be looking for gadgets in here. Luckily, it just gives us the full path to it. So we'll just do wrap gadget binary address, put it into gadgets, and give it like 5 years to load. really should just edit this out. All right. Well, never mind. I'm lazy. So that's why you save it to a file, so you have to always like look at it again. So also, let's just take a look at gadgets. I'll just look for like pop. Okay, sure. So before it was giving us full addresses, now it's giving us offsets because it doesn't know what the address will be when it's finally mapped into to our program. It could be anything because of ASLR. But what's giving us is the same offset that we were using here, which is just from the base. So just like here, we're subtracting this, we would just add the base, add the offset to the base of libc. Let's look for, well, actually first, let's just like run the program and see what's going on. So here, we're getting that same thing from before, invalid SP address. So luckily, we have, we want to just put our stack pointer there. We don't know the address, it will always be different, but we've leaked it. So now we can just do route chain plus equals whatever, blah, 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 buffer, which is just our stack address. And now we'll do route chain C times 4. So, cool. Oh, right. So now, because we're overriding the, here, I'll just step through it actually with a breakpoint. All right, so let's step through it. So here is, so if we look at our running program, 36do. So this is at the end of our whatever buffer we put in this, the address of where we want, like whatever, we put the address of where our buffer is, overriding where we want the stack to go. So this is kind of what's called a stack pivot. A stack pivot is basically where you corrupt the stack pointer to pivot somewhere else. So like normally it's just like there's a region of memory that's like this is where the stack is supposed to be, but you could pivot to like literally anywhere that you have like read write permissions to. In this case, we're kind of just pivoting like a little bit. So it's still like kind of around the same area, but you can pivot to like, a buffer, like on the heap or something. It doesn't, it doesn't really matter. There's no like hard rule that it has to stay there. So first, we kind of saw this before, but it pops ECX. So pop ECX, which is our pointer to our buffer because we put it there. Next. Okay, so now it loads the whatever that address that we put in onto the stack -4. So now it returns. So originally ECX is pointing to the beginning of where our A's are. Now because of the -4, it's going to here, and there's just like some zeros. So we want to add 4 to make sure that it's actually going to be on our A's. So now we'll step a bunch. And sure enough, now it's on our A's. So we can now just, before we were writing our route chain after the buffer, now we can write our route chain literally in the buffer. That's kind of annoying though, because then you have to make sure it's always like, add padding, so it's always 64 bytes, because you need this thing at the end to be in the right spot. So what I'm going to do is actually just add another 64 or 68 rather to hop over this thing. And now we'll just put route chain C times 4. And now we can just do it normally, so we don't have to like really worry about all that stuff. So now we get to our C's. So yeah, pretty straightforward. So now we want to start going through and just replacing those gadgets. So we'll look for AX ret in our gadgets. So, okay, cool. So there's one at this offset. So before we hard coded it, now we're just going to take the offset, add libc, and then times 11 like normal. Also, we should probably not have that there. Now let's take a look what happens when we run it. That is a weird looking buffer. Whatever. So now instead of our C's, we have our inky AXs. So just step through it. Let's just do 11 of these, and then get to our C's, and then that's where it dies. So that's great. Now we want our pop EDX ECX gadget. So we'll do cool. So it's over here at this offset. And we want to put stuff for it to pop into our registers. So we'll put 2 zeros like before. And we'll just do a placeholder like before as well, because let's just make sure everything is sane before filling it in. And now that should be fine. It should pop our registers, and then now we want our int 80. So we'll grab through, find it over here, got the offset like before. And perfect. And now we'll just do rob chain plus equals sh, because we want to have that somewhere. Actually, I'm going to not do that, and I'll show you a trick later. So step through, increments, blah, blah, blah. Okay, we have our pop3 registers gadget. So it's EDX is 0, ECX is 0, EBX is now our A's. Int 80 does nothing because it doesn't know what that string is. If that ever happens, if you do a syscall and it doesn't work, you can also just look like EAX will have like an error in it instead of just like whatever. So yeah. What I wanted to show you was that if you do find, there's actually a binsh string already in libc. So rather than having to put it in the program yourself, you can actually just like use this. So because this is in libc and we already have, it's always going to be at the same offset from the base of libc, just like with everything in libc. And we know where the base of libc is because we have our leak. So we can actually just do that, get the offset of it, do the placeholder. I'm so bad at typing. Okay, step through, pop our stuff. Okay, now, so you can see, it's actually a legit pointer to binsh and does our int 80, and now we have a shell. Awesome. So yeah, we had another mitigation on ASLR, and we still were able to pop the program and get a shell. Obviously, it's a little bit contrived. Most programs don't just print out where stuff is. libc and buffer like wouldn't just be printed out like if you're trying to pop like something in the real world. But the next exercise, which I'm not gonna walk through, I'm just gonna kind of leave it open for you to try to solve on your own. But you have to kind of get the leak yourself. It doesn't just print out an address, but you kind of have to trick the program into printing out a memory address to, or leaking something unintentionally using that leak. So I'm just gonna skip the next few slides to this one, or I mean, yeah, do Route 3. But then this one, which is basically just like these are a list of really, really great websites for doing more challenges like this. So the ones that I've been kind of demoing are pretty basic, kind of just to teach the concepts. But these websites have really, really interesting challenges that are really fun to solve that range from like really beginner ones that kind of show you the basics to like crazy stuff that when you solve it, you'll feel like you're in a movie hacking into, you know, the CIA or whatever. So definitely recommend checking those out. Also, CTFs are great. War games are basically all go as you want. So you just make an account and you solve challenges and whatever at your own time. CTFs you kind of need to pull an all-nighter for a weekend or whatever. You don't have to, but it's just more time pressure and you only have like a certain amount of time to solve the challenge. So they're also a really great way to learn if you prefer learning under pressure. They're really, really fun too. So yeah, definitely ask some questions on Slack or IRC. Um, thank you.